plan.
Okay. So as I said, this is just for bonus. This is just to learn something cool, something interesting, something about chemistry that maybe you didn't know. I mean, some of this will be a little bit of review of the very beginning. Yeah, this is a quote from Homer Simpson. Thank you, most of all, nuclear power, for which is yet to cause a single proven fatality, at least in this country. So, yeah. All right. So, back in Chemistry 111, we just talked about the discovery of the atom, the nucleus, the electrons. And when we talked about that, we mostly focused on the electrons because in all of our chemical reactions, electrons were where it was at. But in nuclear chemistry, we really need to focus on the nucleus itself. That's the nuclear reactions. So it's going to worry about like the protons and neutrons together. And together, those are known as nucleons. But just quick refresher, call our atomic numbers just the number of protons, our mass number the protons and neutrons. And the concept of an isotope is the same atomic number, same number of protons, different number of neutrons. So it weighs a little bit more or a little bit less. So we need both protons and neutrons to make a stable nucleus. Protons kind of have the attractive force between the nucleus and the cloud, but protons are naturally going to want to repel each other. Protons are a bunch of positive charge jammed into one nucleus. And so in order to keep this repulsion at a minimum, you need these neutral atoms kind of shoehorned in there. If you have a weak nuclear force that's going to hold these guys together. If you have too many protons, it's going to be too much repulsion. They're going to shoot out. Too many neutrons, and it's going to still they're going to explode outwards. These guys will break apart. They will radiate particles until they reach a point where they're at a stable number again. This is what's known as our radioactive decay. We see a nuclear changes that changes one element to the other. This is the only way we can turn lead into gold, by changing the number of protons and neutrons in there. That's what makes an element an element. Not the number of electrons, simply the number of protons and neutrons are what's going to make lead have this property and gold have this property. So if you were somehow managed to shoot the lead molecule with enough energy to just break off, lose like 4 protons and enough neutrons, you could hypothetically turn lead into gold, but that's not likely to happen. Not too easy. Now, some elements, as we'll learn, are always radioactive, no matter what. We cannot stop that. Uranium is one of them. Plutonium is another one. But some of them only have certain isotopes that are radioactive, like carbon-14, which thus it's called a radioisotope. So some of those guys we're going to use in some of our nuclear science, like when you talk about medical radioactive therapy, where you inject a radioisotope into the body for either imaging or other sources. And like radioactive iodine is used to treat thyroid cancers and help image the thyroid. So using a radioactive isotope of something that's already going to be taken up and drawn into the thyroid. Okay. So 3 of these types of decay we've talked about when we talked about the basic atoms. We talked about alpha decay, where alpha particles are shooting off essentially a helium nucleus. That's 2 protons, 2 neutrons, no electrons. It will have a mass of 4, and a charge of 2. So loss of 2 protons and 2 neutrons. It's a big, chunky loss. A beta decay is when we essentially shoot off an electron. It's essentially no mass, but a -1 charge. And we talked about gamma, which is just energy, just like cooling down. Like an atom can undergo gamma decay when it has too much energy and just needs to work some of it off. It's like when you emit light. It's just a very high energy loss. But the positron is something that's new. And this is kind of a weird. It's a positive electron for all intents and purposes. It's not a proton because it has no mass. It's literally like a positive electron. We shoot off something that has 0 charge, a +1 charge, but 0 mass. So it's the anti-electron. So proton is not quite the anti-electron because of the great difference in mass. But the positron is literally like a positive electron. And the last thing we can talk about is electron capture. It's not an actual shooting off of particles, but it's more like something that happens within the nucleus itself. It's when an electron kind of decays from its orbit and spirals into the nucleus and gets absorbed into there. So electron is lost, but it's not shot outwards. It's going into the nucleus to add a charge to the nucleus. So what happens when these things occur? The parent nuclide, which is our starting reagent, will undergo one or more types of decay, releasing these particles, but it will produce a new element, or at least a new isotope, which we were going to call the daughter nuclides. So it could be it fractures into several daughter nuclides and one of these particles, or it just produces one, like say alpha, and then whatever undergoes alpha decay from lead to mercury, for example. But so the first thing we can do is we're going to do math with this as we look at what kind of chemical reactions we have. So this is just a nice table to see what's actually occurring. Alpha decay could be abbreviated like this. More often, you're just going to see it like alpha. Simplest decay, don't have to think too much. A proton and a neutron are just directly ejected out. Most common one, here's radium. Radium ejects alpha. And so note, it goes from 226 to 222. 222 plus 4 is 226. It goes from 88 to 86. 2 plus 86 is 88. So notice, the sum of all protons and neutrons add up to the original parent. All of this energy is conserved. Now a beta, we're kicking out an electron, but this electron is not coming from the electron cloud. This electron is actually coming from the nucleus. So how do we generate an electron from the nucleus? Well, a neutron could be thought of as a proton plus an electron. That a proton has the same mass essentially as a neutron, and it has a positive charge. The electron has almost insignificant mass, but it has a negative charge. Add those two together, they cancel out to give you the beta, the neutron. So if a neutron splits apart, it could split into a proton and electron, which is then ejected. And that's going to cause a loss of a change in atomic number without a change in atomic mass. So a beta particle moves us one to the right. So iodine, essentially when it kicks out an electron, goes to xenon, a noble gas, while having the same mass number, 131. A gamma is just excess energy. It's often released as electron relaxes. it's often lost with other stuff. So cobalt can undergo beta decay and gamma decay to form high energy nickel, and then the nickel can emit more gamma rays as it calms down. So it's eventually like hot nickel cooling down as it releases this energy back out. Now the positron. So if a positron, this is kind of weird, if a beta particle is a neutron breaking apart, a positron is a proton breaking apart, and when it kicks off its positive charge, it reforms a neutron. So it breaks apart to a neutron and a positron. So it kicks off its positive charge but keeps its mass and loses that as a positron. So we see carbon 11 kicking off a positron to become boron 11. So a positron moves us one to the left. And finally, electron capture. It's actually going to be very similar to a positron. The orbital electron gets sucked into the nucleus, combines with the proton, and forms a neutron. So proton plus electron gives us our neutron back. So rubidium absorbs an electron from its nuclear cloud to form, moves us one to the left. Rubidium to krypton. So all these are things you don't really need to know how it happens, but the point of this talk right here is to try to explain some of this cool stuff of how it actually happens. If I were to test you on this stuff, it would not be how it happens. It might be able to do this math. If I gave you the standardized final, there would be one of these types of problems on it, but I'm not giving you the standardized final. So no matter what, even if you have a final, you're not going to have the standardized final. So practice. So what it takes us to do is to, there's a typo there. I'll have to fix that later. What you need to be able to do is put together the products, the daughter nuclides based on these losses or these types of decay. And literally you want to look at your periodic table. You want to hold that up in front of you and look at, I haven't given you the atomic number of these guys, so you have to actually look up your atomic number to help you. But, so for example, sodium would be atomic number 11. If it were to lose a beta particle, that should be beta particle plus something, not beta plus. It's not a chart, that's a beta, not a positron. So if this is 11 at the beginning, the sum of all the atomic numbers should add up to 11 on both sides. So if we have a negative on the right and just a straight up 11 on the left, we must -1 plus 12. So meaning it's going to move from sodium to magnesium. Now the mass of magnesium would stay the same because 24 plus 0 gives me 24. 24 mass, 24 mass. So this would be, so the first product is going to be Mg24, 2412. So that's our first product. Now, boron. Boron is 5. It's undergoing positron decay. So positron means, so I'm going to say we have an element X, 0, and we're going to do Y, Z. Let's add up y plus 0 equals 8. So y has to be 8. 1 plus z equals 5. Z has to be 4. Now, what element has the atomic number of 4? That's going to be what? Beryllium, I think. So I am determining my element by my atomic number. We don't know the element until we see this guy. Actually, I'm going to change that color because red doesn't look too good on that. Iodine. Iodine is 53. There we go. 53. So now we have our element X with a mass of Y and an atomic number of Z. 125 plus 0 equals 125. 53 plus negative 1 is going to be 52. Element 52 is tellurium. So I'm using this guy as my scheme of what I have. Finally, francium. Francium. Oh, francium is down in the fancy lanthanide and actinides. If I'm not, no, I'm wrong. Francium is bottom left corner, 223. Oh, sorry, no, that's 87. I'm looking at the atomic number, the atomic mass, 87. If that undergoes alpha decay, so here's the only way we're losing mass. Y plus 4 is 211. So that means we have 207. Z plus 2 is 87. So 85. And that moves us to astatine. Astatine. So first clicker question. So once again, feel free to send me an email. Identify what particle would we need to lose to make this nuclear equation correct. Phosphorus mass 32 is going to sulfur mass 32. What would we have to kick out to form that? Reading about nuclear reactors, so I'll be able to give you all the lowdown of what you need to know. Okay, give it 2 minutes. As I said, if it's not working, send me your emails. Send me your emails. I'll gladly deal with them that way. Okay, so we need to have something that has 0 mass, but a -1 charge. So that's 16 plus -1 comes from 15. The answer should be B. B. So we want proton would have 1 mass and 1 charge. A neutron would have 1 mass, 0 charge. So we'd see the loss of a, actually we'd see a loss of a neutron as it breaks into a proton. Okay, apparently we're at 10:25, but I'm going to go a few more minutes, go to another slide before I stop and restart, since we started right on time. Oh, yeah, we'll do another clicker, and that's where we'll stop. So, describe what must be occurring in this nuclear reaction where bismuth goes to polonium and forms that. So this one's a little bit harder. A little bit harder. You got to think about it. What does a helium atom look like? What does it mean when an electron is captured? What is a positron? What is a proton made up of? What is a neutron made up of? But this one, as I said, I would not ask you on a test, but still a very valid question. Minute or so. Expect at least one more response. We had 8 for the last one, unless it kicked you out. It to 145. So another 5, 4, 3. There we go. 2. So here. Okay. So in this case, what we see here, not a loss of mass, but a gain of atomic number. So a neutron is being converted to a proton, kicking out a beta particle. So nothing is being captured here. We're actually, a neutron is turning into a proton as it kicks out a beta particle. But technically a neutron, if it captured a positron, would turn into a proton. Okay, we're gonna, this is a stop share in this recording, and I'll resume. And okay, so now one of the main things to worry about is what's called as a radioactive series. That many naturally radioactive elements do not undergo only one decay, but actually a series of decays. They'll undergo what's called like a radioactive series, where it'll undergo a series of alpha and beta decays, and of course some gamma decays until it reaches what's known as a stable nuclide. And so essentially, like looking here, starting from uranium-238, undergoes an alpha decay, which gets it down to 234. And then it goes 2 beta decays, gets it down to uranium-234. So essentially what happened there in those first 3 decays is it just lost mass without losing atomic number. And then uranium-234 undergoes an alpha decay, gets us down to what, like uranium to thorium, then from thorium to like radium, radium to radon, radon to bismuth, bismuth to what? So no so not bismuth, but polonium, polonium to lead. Actually, I missed something. No, uranium, thorium, radium, radon, radium, radon, polonium. What? I don't know what's going on with my brain right now. I'm missing something. But it essentially undergoes a series of decays. Let's see. On here, that's 92. The 90 would be thorium. Then 88 would be radon. 86 would be, oh, sorry, radium. 86 would be radon. 84 would be, oh yeah, I was right. I was right. I'm just driving myself insane. 84 would be polonium. And then that's lead 214. But lead 214 isn't stable. So lead 214 has to either undergo 2 beta decays, then an alpha, 2 betas and an alpha. Or it undergoes a beta and an alpha, and then 3 betas and an alpha. No matter what, this is the stable nuclide we end up. All these guys along this chain are not stable. Well, maybe bismuth. I don't know why they wanted to especially mark out bismuth in here, but all these guys, in fact, when it comes down to this, uranium-238 is the most common form of uranium. And because it decays down to lead-206, which is not the natural, most abundant form of lead, lead's, phone keeps on turning off. My lead's, what the most common atomic number is 207, maybe a little bit closer to 208. And so by looking at this isotope of lead, we can actually determine how much uranium was present in the material. And also, this is going to be something when we talk about kinetics again, determining how old is a rock by measuring how much uranium is still left and how much of this lead-206 is present in that rock. So how do we actually measure this radioactivity as it undergoes all of these series? We can measure these in disintegrations, which is essentially a particle emission, as particle emissions per second, also known as the activity. Now the units of these are, all these crazy units we're going to see are named after usually the scientists that did this very important work when they first discovered radioactivity. So we have Berkel's, which is a disintegration per second, and a Curie. Maybe you've heard of Madame Curie. She is one Curie is worth 3.7 times 10 to the 10th Berkel's. Now, Curie, this seems like a very unique conversion, but a Curie's measured the radioactivity of an radium, which is one of the key elements she discovered. So, how are they actually measuring this? Are they actually determining this radiation? So we're seeing ionizing radiation coming from the specimen. It's going into this little tube filled with gas atoms. And as these gas atoms are being hit by these ionizing radiation, they are kicking off electrons and protons. And protons are being attracted to the negative wall of the probe, and electrons are being attracted to this wire in the center. So, and this wire is then able to detect this charge as they're separating. This is essentially, we're doing a electrochemistry reaction, but the spark is here, the radiation, not the not running a current through this. This is not naturally occurring electrochemistry, but and then so we can measure this, like how much gas particles are being ionized to determine how much radioactivity is present. That's how we use the uh, that's how you typically measure the radioactivity of an area. As you're waving around this little wand here, the wand is essentially picking up this ionizing radiation being flung into that little wand. Now, within these radioactive chains, there's a certain stability diagram. Now, normally, as I said, protons will repel each other, but there's a strong nuclear force between our protons and neutrons that are going to hold the nucleus together. Hard, fast rule, atoms with protons between 2 and 20 will have about equal number of protons and neutrons. So, up to like what? Like to say a little past argon, maybe calcium. You have you see the mass number is literally just double the atomic number for most of these guys. But above that, you start to get more and more neutrons. As you're building the nucleus bigger and bigger, you need more and more neutrons to try to shield the protons from each other. And eventually you reach a point where there is no amount of neutrons that will make this stable. Lead-82 is the heaviest element with a stable ratio of neutrons. So anything heavier than lead is, by definition, radioactive. Polonium, astatine, radon, francium, radium, all these guys are, everything past lead is radioactive by default. There is nothing that's going to make that stable. Now, some of these guys will be more radioactive than others, but many of them are going to be highly radioactive. Now, there's a stable ratio known as the belt of stability, which we can use to predict the decay pattern. So all these little dots right here is this belt of stability. Right here, this red line is where the amount of protons and neutrons are the same. So you see at 20 to 20, this is pretty close to that line. There, but past 20, so there's a bunch of different stable neutron isotopes in here. A bunch of different stable isotopes in here. As long as there's one guy on this line, that's true. Once you get past 20, it's deviating from this line as it moves up to greater and greater number of neutrons. Now, based on where this is on this line, you can predict what type of decay it's going to undergo. So, thinking here, if I'm right here in this green area, looking at here, I have to get down to here, I'm always going to have to lose something. I'm always going to be moving at an angle towards the baseline because I have to lose a neutron or a proton and gain a neutron. So I'm always going to be moving at a diagonal to get back to this line. So as I'm going here, I'm going to convert a neutron to a proton as I undergo beta decay. And that's going to give me, each beta decay is going to move me one more down and then one more down until I get to one of these stable areas. If I'm over here, I'm suddenly below to the line and I have to go up. So I have to convert a proton to a neutron. And those are going to be positron decays. And you're going to go positron decays where we convert a proton to a neutron, or electron capture that converts a proton to a neutron. So I'm going to be moving up at an angle. So all these guys, if you're too far to the left of the line, I'm going to go beta. If I'm too far to the right, I'm going to undergo like some sort of positron. And then, of course, if I'm above here, there is no possibility of finding a stable region. So how do we get down? We have to lose both protons and neutrons. So when we undergo alpha decay, we're moving diagonal down left. That's going to move us from here to there, to there, to there, until we get to one of these stable regions. We're going to undergo alpha decay until we get to a stable region. Because essentially we're trying to find this magic number of protons and neutrons that keeps everything happy, keeps everything stable in the long run. And so that's a lot, controlling a lot of our radioactivity and why it undergoes this decay, not that decay. Why does it undergo beta and not positron? Because we have this magical belt of stability here. Now there's some math involved with that, but I don't know the math really well, and I don't think we really need to know the math real well, but it's kind of like a magical ratios of math, kind of like our octet rule, where we know that, oh, if I fill out 8 electrons in here, it's suddenly really stable. Or if I fill in 10 electrons into the d orbitals, that's really stable. It's kind of like that same idea. Some magic numbers. So this is just reiteration what I was just talking about. It's above the belt, which means too many neutrons, and go beta emission. If it's below the belt, too many protons, we either go positron or electron capture. Now here's a quick fact. Light nuclei, because they don't have as many electrons, will undergo positron emission. So if they're not too heavy, they'll probably kick out a positron. But if they're really heavy, like iodine, they have a ton of electrons, they're going to undergo electron capture instead. So like carbon and whatnot will probably go positron, but if I said like, oh, selenium or bromine will probably undergo electron capture. And of course, any nuclei above 84 will go through alpha decay. Now, this should remind us of chapter 14, our kinetics. A radioactive decay undergoes a very regular pattern, regardless of whether we go in alpha decay, beta decay, positron, electron capture. It's going to be a very, very regular pattern. These are all going to be first order decays, in which there's a constant time interval. Our half-life for these guys were, for first order decays, were ln2 over k. So our constant, or our radioactivity, ln2 over that constant. Our half-life, and it's very, very regular. So if your half-life is 2 years, 1 gram would go to half a gram after 2 years. After another 2 years, that half gram goes to quarter gram. And then that another 2 years, that quarter gram goes to an eighth of a gram. And that's part of the problem with radioactivity, is that you're not really, you can't really speed this up. There's not a way to really make this go faster. You just let it sit, and it's going to keep going half and half and half under that same period of time. Of course, each radioactive element will have its different half-life. So, but it's all going to be first order decay no matter what. Which gets us to carbon dating. So, we cannot speed this up. We cannot change the rate of decay. And for most of these guys, the rate of decay is pretty well known. And this is how carbon dating works. If you've ever heard of it, we're trying to determine how old this fossil is, how old this this artifact is that we're going to determine how much carbon-14 is present in there. So how does carbon-14 come into being? Play first. So the sun is going to constantly be giving out cosmic rays. Some of these cosmic rays are going to reach through our atmosphere and hit nitrogen. And when they excite the nitrogen, we essentially see nitrogen being converted into carbon. Essentially, how would that happen? It would have to undergo what, like positron emissions? Have to give off one of its protons without losing one of its electrons, without losing one of its neutrons. So it forms into carbon-14. So we have essentially a CN bond, which then, through different chemical processes, gets turned into CO2, carbon-14 CO2. Now, as we all, hopefully you've had some biology, that plants will absorb that CO2 as they go through I'm not going to say what cycle because I can't remember right offhand whether it's the Krebs or whatever. I'm not going to try to make too much of an ass of myself, but just that plants will respirate in the CO2, they'll absorb it, put it into their bonds. So they'll have carbon-14 present in their plantness. And of course, animals will eat the plants and incorporate that carbon-14 into their cells. And of course, we are going to eat the animals and it gets incorporated into us. The basic idea is at any given time in history, there's a certain ratio of carbon-14 and carbon-12 in all of your cells. You're slightly mildly radioactive at all times. Not enough to really be noticeable, not enough to really care, but we have a little bit of carbon-14 in us. Now, carbon-14 is decaying all the time, but it's pretty slow. Pretty slow. And so the basic idea is that for all intents and purposes, you'll keep the same ratio of carbon-14 in your body for the entirety of your life. The problem is, when you die, or when whatever dies, you're no longer going to be absorbing any more carbon-14. And now the clock starts. So carbon-14 can only decrease at this point. So the half-life of carbon-14 is approximately 5,700 years, meaning every 5,700 years, the ratio of carbon-14 to carbon-12 was, let's say there's 2% carbon-14 in there. Now suddenly maybe there's 1% carbon-14. Then after another 5,700 years, maybe there's only 0.5% of carbon-14, and so on. And because we can measure the radioactivity of this carbon-14, and we know what the average ratio of carbon-14 should be, we can approximate the age of certain fossils. Like if you find a Viking longboat and you find some wood beams intact, you can approximate when that tree was cut down to make that beam, because as long as we can measure the carbon-14, we can figure out how old that is. Now, there is a problem. Objects older than 50,000 years get a little iffy, because when you're measuring fractions of fractions of fractions, when you're measuring something where it's such a small change within the half-life, you come into, remember, our significant digits and our error, and it's hard to know approximately how much carbon-14 was lost. So when we get too old, it doesn't quite work. But it works to some extent. Now, that's how the same generalized process is how we determine the age of the Earth. How something, say this rock is this many millions of years old, because this rock contains natural uranium-238, and it contains this special lead that came from uranium. So we assume when this rock was fully formed, it was this much uranium, because I can convert all the lead plus the uranium plus all the other byproducts into all being uranium. So all the sum of all these decay products add up to being how much uranium we started with. Now, if I measure how much lead we have and how much uranium we have, and there's there's some mathematical ways we can calculate this, but it's the same general process. If I can figure out how much of each of these products, I can know how many millions of years must have gone by to get this much lead. Now, that's not to say that rock may not have come from an asteroid somewhere out in outer space, but if you find a rock pretty deep in the Earth's crust, you know, well, that rock had to at least been buried for this many millions of years. Even if that rock is from outer space, this layer of Earth must have been here for that many millions, this period of time. So we can try to figure out the age of the Earth based on some of these samples of rocks. Now, how are you going to calculate a problem if you were to do this? If this was on a test, you'd have to do the kinetics again. Not too bad. It's not really that hard. If you knew how to do kinetics for the first chapter, you can do it again. The differential equation is just the rate is equal to a constant times the number of radioactive nuclei. We're going to then integrate the rate law to say the natural log of the nuclei at time t over the nuclei at time 0 equals negative k times the time. So you could calculate how much time has passed by looking at the nuclei we have versus the nuclei we started with. And of course, all radioactive nuclei, k is equal to ln2 over t1/2. So all that is something we talked about in chapter 14. It's just now we're specifically looking at radioactive decay. So, hypothetically, a 500 kilogram drum of uranium-238 is stored for 1 billion years. How much uranium would be left after that time? And here's where it's depressing. So 4.5 times 10 to the 9th years. That's the half-life of this bastard. So ln2 divided by the half-life, 4.5 times 10 to the 9th, you get a K that is 1.54. So I'm going to say our half-life, ln2 over 4.5 e to the 9, you get a K, which happens to be a really small number, 1.54 times 10 to the negative 10. And I want to say, well, a billion years. So 1,000 is 10 to the 3rd. A million is 10 to the 6th. A billion is 10 to the 9th. So how much is left after 1 billion years? You're dead, your dog's dead, your whole family, and possibly most of the Earth is dead after 10 to the 9th years. ln, we'll say nt over 500. So we're going to take that number times 10 to the 9th times -1 and do the inverse log. We're going to multiply that by 500 to give us how much is left. So how much is left after a billion years? Well, 428.6 kilograms. That's how much is left. So quite a bit is still left. How long would it take to get to 1 kilogram left? So this one, I'm giving you a n sub t, and I'm saying how much time? 10 to the negative 10. Okay, well, for God's sake. So ln of 1 over 500, and we're going to divide by, oh jeez, hate you, Cortan. Let's stop it. Okay, divided by 1.54 e negative 10. So it would take close to 40 billion years. So 40 billion years, and then would only have 1 kilogram left of our original 500 kilograms. Hopefully you can kind of see why. I mean, nuclear power is a great thing and a promising thing, but we have to, just like alternative energies, we have to think of a way to make this work for us. So if we let this go through a natural process, you have to think really, really, really long term. And we have not been good at thinking long term a lot. We can't even think about like our environment now a year in advance half the time. Which was like, yeah, dump it, whatever, we'll figure it out later. And then we have to go and clean that up. In a couple of years when people start like getting cancer because we dumped a bunch of waste in the wells. So yeah, we'll do this clicker question, and that's where we will stop for today. Okay, the half-life of iodine is 8 days. Half-life of this iodine is 8 days. How long would it take for the sample to decay to 25% of its original level? So, not meant to be overly tricky. Got to think about it. Think about what that means, what half-life means, and all that. But as long as there's not a clicker on the next slide, this is where we will end today. A few more minutes. You don't actually have to use your calculator, hypothetically. That's what I try to do. These clicker questions are trying to be very low math. If you have the time, give it to 1:45, so 15 seconds. Half-life 8 days. How long did it take to get to? One more, and oh, stopping. Okay, so if it took 8 days to go to 50%, it would take another 8 days to go through another 50%. So 8 days to go 50%, another 8 days goes to 50% of 50%, which is 25%. So it takes 16 days. Okay, so let's make sure there's not a clicker on the next. Okay, yes, this is where we will stop. Next slide, next couple slides, we're talking about how we make some of these neat new elements using this idea, and we'll get into what nuclear chemistry of like how does a nuclear reactor actually work, some process. I might actually update these with some of these images if I find something particularly good in this little like pamphlet I'm reading. So hopefully I'll have that all ready for you next class. Have a good day. Once again, like, subscribe, yada, yada, yada. Work on that test.